Today, we are going to talk about how the position of layer norm PreLN versus PostLN affect fine-tuning performance in low-resource settings. Transformers are widely used in NLP because they handle sequence well and allow efficient training. But even in transformer training, stability is still a challenge. Previous studies have shown that PreLN help with training stability and faster convergence. But most of those study has using large data set and powerful hardware. So here's our question is which structure pre-LN or post-LN work better when we have only a small amount of data? That's the main focus of our study. Our goal is to find out how layer norm placement affect translation performance when training data is limited. We know pre-LN work well in large-scale model, but what about low resource conditions? That's what we wanted to explore. To answer this question, we use the transformer encoder-decoder model. It's a sequence-to-sequence architecture. It's also used self-attention with help with long-range dependency and parallel computation. Each layer in the transformer uses residual connection. This helps gradient flow smoothly through the network, making training more stable. Our comparison pre-LN versus post-LN is based on where the normalization is placed in this residual path. Now let's look at the key difference in the PostLN structure. Layer norm is applied after the output of block. PreLN normalization is the input before each block. We use the Opus book dataset from Hugging Face. It is English to French sentence pairs. We split the data 80% for training and 20% for validation. Then we using 500, 1,000, and 5,000 sample to evaluate translation quality. We use a fixed set of 200 validation sample for blue score. For pre-processing, we use T5 tokenizer. We set the max token length to 64 to match average sentence length and reduce memory cost. For shorter sequence, we apply padding so all input had the same length. We use T5 Small, a lightweight transformer model with 60 million parameters. It has 6 encoder and 6 decoder layer and is often used for task-like translation. We loaded the pre-trained weight and fine-tuned it on our small datasets to see how structure changes affect performance in low resource settings. We compare two versions. The pre-LM version is the standard T5 small model. It uses Hugging Face auto model for sequence-to-sequence LM, and layer norm is applied before each sublayer. Post-LN is custom versions we modified. Layer norm is applied after each sublayer. We changes the internal structure and loaded weight with strict equals false. This allow use to test if changing only the layer norm position make a difference. We tested with 500, 1,000, and 5,000 sample. Pre-LN use a learning rate of 5E minus 5 and no warm-up step. Post-LN use 1E minus 5 and added warm-up step to improve stability. Warm-up step was set to about 5% of total training step in each scenario. Epoch were adjusted by dataset size. Other settings like batch size and optimizer were kept the same to ensure a fair comparison.
Here we present the result from the 500 samples conditions. The left side shows the pre-LN and the right shows the post-LN. This slide presents the result from the 1,000 sample experiment. This slide presents the result from the 5,000 sample experiment. This table summarizes the final blue score by sample size. PreLN shows state improvement as the amount of data increase, but PostLN does not. This suggests that PostLN failed to run meaningful translation under all conditions. This slide shows the loss trend with 500 samples. The left shows the PreLN and the right shows the PostLN. This slide shows the loss trend with 1,000 samples. Here we see the trends with 5,000 samples. When we summarize all loss value in a table, it shows the PreLN trend both stable as the amount of data increase. In contrast, PostLN shows almost not learning progress due to structure issue or failed initialization. The goal of this experiment was not just to compare performance, but to see how its structure behaves in lower resource settings, and how structure compatibility affects learning. However, PostLN revealed two main issues. It failed to produce meaningful translation and lacked training stability. There are two key cases. First, incompatibility between pre-training T5 weight and PostLN structure. Second, limited data made it hard for PostLN to converge probability. PreLN consistently converged under all conditions, and Blue score improved with more data. In contrast, PostLN shows low Blue score and high loss, this indicating poor training result. This analysis confirmed that the position of layer node is just a structural detail, but directly impacts training stability and performance. A low resource fine-tuning PreLN is clearly more suitable. And here is a reference, and thank you.